test the electrical resistivity, you can test how fast, if the concrete have higher resistivity, this means it can resist the amount of chloride that will pass the concrete. So the higher the resistivity, the durable the concrete, and the higher or less corrosion that will happen to the concrete. So this is the essence of measuring electrical resistivity. Then RCM test, that is using rapid chloride migration test. There is a method that we call rapid chloride migration test, NT built 492. We conducted it using like a cylinder of 100 millimeter diameter with thickness of 50 millimeters to determine chloride migration. Then after the taking the test, then we use silver nitrate and test the depth of the chloride. So this is the arrangement. If you see this diagram, this is the arrangement of the stainless steel. These are the specimen A. This is the specimen, the concrete that is used. If you see, you can see some block with embedded fins inside it at different area. This is the LCR meter. This is the concrete connected with the LCR meter. So this is the diagram for rapid chloride migration test using NT built. This is the specimen. As I said, it is 100 millimeter with 50 millimeter depth. So this is the machine that we pressurize the concrete. That there is a preconditioning that we do. Now here is where we put the concrete inside calcium hydroxide to spend some hours. This is where we keep it under pressure for some hours also. This is where we are taking the test. The below, the concrete at the down.
Yes.
We can.
Okay.
Sorry for the little hitch.
Yes, it's okay. We cannot control it. It's beyond our control. So, can you see my screen, please?
Yes.
Okay. So, let me continue where I stopped. So, this is the samples. Below the samples is a sodium chloride. At the top of the sample inside the tube is a calcium. Sorry, at the top is sodium chloride. At the bottom is calcium hydroxide. So then we induce electrical resistivity, electrical current. So we like pressurize the chloride to penetrate into the concrete. There is certain method, there is method procedure that we follow in order that amount of current to use, time. So after the test, then there are some table that you can know how much current are you going to inject into the concrete and hours that you are going to take. Then you put the silver nitrate and test. This is the penetration. Where you see white is a sign of chloride that passed through the concrete with silver nitrate. The precipitation, white precipitation is a silver nitrate. This color brown is a concrete itself, where there is no chloride. So we measure we take the average. We took the average of the penetration and then report it. So we did all for all the materials. That is PC. This is the mix ratio or the amount of concrete that we use. This is for concrete with 0.55 water binder ratio. This is for 0.4 binder ratio. This is the chemical composition of the material. We took it to the lab and tested the oxide inside the concrete. So, yeah. So result and discussion. So electrical resistivity of concrete, I just reported here for 28 days. That is, we measure for like more than 1 year. We have been taking it for more than 2 years, I think. So, but here I just reported for 28 days. The reason of taking for 28 days, because concrete, normal Portland cement concrete, gain its maximum strength at 28 days. Any test that you have to carry, you can carry it at 28 days. It reached its maximum strength or optimum strength at 28 days. So that's why I use 28 days here. I report for 28 days here for easy explanation. So it was measured at 10 millimeter depth as I said, we embedded different pins at different depths. So here I reported for 10 millimeter and 40 millimeter. The reason of using 10 millimeters, because it is close to the cover of the concrete, so you can easily assess it and see. 40 millimeters, most of the concrete cover, like here in Europe and UK, they use 40 millimeters, especially in chloride ingress environment. For normal environment, non-aggressive environment, we use 25 nominal cover is 25 millimeter, especially in Nigeria. But here, nominal cover, because they have salty, they are close to the sea as coastal area, because there are some of their structures at tidal zone, some at like when we say tidal zone, that is close, where the sat used to intrude into the structures and cause some problem. That is what we call airborne, and we have tidal zone or splash zone, where the structure is close to the sea. The water can come and go and touch the structure. So they use sometimes they use 40 millimeters depth as a cover. So the result is piece to concrete has lowest electrical resistivity, around 25 to 38 among all the mix. GGBS has high resistivity when we compare it with normal Portland cement, normal concrete that we use normally, around 100 to 170, almost 4 times. Then FA has 70 to 140, 142, even greater than, even greater, always, or almost also greater than what? PC, but is less than that of GGBS. So this indicates improved in pore refinement, indicating improved pore refinement. When we say there is a pore spaces in the concrete, so we want the concrete to be, those pore spaces to be tortuous, to be like non-accessible, to be closed. So this is saying that there is, if less chloride ions pass into the concrete, this means there is less porosity, less porous concrete. So then LC3, the concrete that is new design concrete, that is LC3, the one with clay, normal clay that is abundant all over the world. That's why we use it. Before we tried to use like alkali activated concrete without even cement, but we found that there is some crack due to some hydration. During hydration, there are some crack due to due to hydration. So those crack, that's why we discard it. We use LC3. That is the one with concrete that is all over, with clay that is available all over as well. So this LC3 have higher resistivity compared with all, with around 170 to 228. So then GGBS LP, the concrete with GGBS and with limestone powder also have higher resistivity, but it is less than that of LC3. This means this LC3 is a good concrete with high electrical resistivity that cannot allow electrical current to pass through the concrete. So this is the table showing the results. Well then, let's see if it's not working. Sorry. So this is the result for the electrical resistivity. This is for PC. This is for GGBS. If you can see from the table, LC3 has the highest, even from the graph, from the chart. You can see this is for LC3, had the highest. So this is for the one at 10 millimeter depths. This is for 40 millimeter depths. In both, the LC3 has highest, and the PC, this is for Portland cement, normal Portland cement, had the lowest in both the charts. So then agent behavior. So there is a way that this resistivity increase all over the time. So this is the power loop, the method of identifying the resistivity at any given time. Let's say you want to test it. At this one, we test for 28 days. So if you want to test the resistivity in like 100 days, 1 year, how are you going to use it? You can use this power loop. The formula, this is the resistivity, the time you want. Let's say time is 1 year. So this is P 360 days. This is P-ref. This P-ref is like reference resistivity we took at 28 days. So this means this is a resistivity at 28 days. T, the time we took, the time is, I say like for 1 year, 360 days, or over 28 days. Then N, this is what you call agent factor. Is an agent factor, the factor that is showing how resistivity is increasing over time. So in our own, we calculated our own agent factor, but there is some prescribed or some given or recommended agent factor using FIB model code. That is the normal code that is used in Europe and all over that is worldwide recognized FIB code mod. That is 2006. It is repeated in 2010, 2015, and we have new version here in 2023 also. Yeah. So, but here we calculated our own because of our own mixture, our own curing of concrete. So this is the agent factor. So you can use this to calculate the resistivity at any given time or any given day. So all SCM concrete gain resistivity faster than PC, as I have already mentioned. Deflecting ongoing hydration, I have already defined or explained what hydration means. And pozzolanic activities. Pozzolanic activities is some reactions that happen due to some chemicals or calcium oxide that happen into the concrete that are, that is inside the concrete. So what we call, that's what we call pozzolanic activities. They also increase the strength of the concrete. So this showing that because of that hydration and pozzolanic activities, that's why what give the concrete the low carbon concrete higher resistivity. So LC3 and DDBS show higher resistivity at later age. So this is how the resistivity is increasing from this graph. I just took for 50 days. The reason of taking 50 days because I took the concrete out of the water for like after 28 days. I took it out because I took many different tests. I do for carbonation and many other tests. So I took it out, but this this resistivity depend on the moisture of the concrete because the concrete, the electrical current has passed through inside the water. If there is no water in the concrete, this means it will affect the movement of the electrical current. As we know, water is a conductor of electrical because of some particles or some impurities. So it takes some charges. So the reason why I remove it from the water, from the curing water after 28 days. So I don't want to take like long time. So that's why I took 56 days in order to avoid that drying effect of the concrete. So this is how the electrical resistivity move. If you see from the graph, the highest one is LC3 from here. The highest one for 0.55 also is LC3. So this is how it keeps increasing with time. This is for PC, normal Portland cement concrete. See the lowest. Here is the lowest. So then rapid chloride migration test. We took the rapid chloride migration test after 180 days. The reason why I do this at 180 days because of the hydration that is occurring in the concrete. So I just want to see the effect of hydration. So I left the sample, that is the cylinder inside the water for 180 days. Then I took the test, then I calculated the depth of the chloride, then I calculated the rapid chloride migration using this formula given by NT Builds. So then I reverted using this method that I told you there is a method factor that you can test or you can revert the chloride diffusion coefficient at any given time, just like that of resistivity. So this one I have for 180 days. So I want to calculate for what? For 28 days. Also, as I did for electrical resistivity. This one, I did it for 180 days, but I converted it to 28 days using the formula, this formula. So rapid chloride migration at 28 days is the reference diffusion coefficient of times 180 divided by 28. Then you use agent factor. We also, for this agent factor, we use this one. This one is the one given by FIB model code because of we found some different behavior in the concrete. So using FIB code and what. But for LC3, there is no agent factor in FIB code model code. So that's why in this LC3, I tested for 28 in FIB code mode, FIB model code, sorry. So, but for LC3, we don't have it. So that's why I tested my own agent factor, because we don't have it in the code. So that's why you see star saying that based on experimental results. So the result of this, PC has 20 to 26 penetration, chloride diffusion coefficient. It has higher. So this, we need small value, because it's the measurement of how chloride can penetrate into the concrete. So this means the higher the penetration, the higher the effect. So we need less penetration, less chloride diffusion coefficient. So if you see from our result, PC has 20 to 26 meters square per second. GGBS has 5.5 to 7.9. FA has 4 to 6. FALP has 3.2 to 7.2. LC3 has 4.1 to 7.9. This means PC has highest value. So this means low carbon concrete has less penetrability of chloride. So SCM markedly reduced diffusion coefficient relatively to PC, consistent across all the binders. Water binder ratio, sorry. So you can see from the graph, this is for PC with highest, see the difference. So this is for LC3. So, but if you can see from the result, FA has the lowest here, but LC3 is between FA, just like it's greater than, it has less penetrability than PC, but what? Higher than lesser than PC, but higher than FA. So this means this we can use this LC3 in making concrete. So then I use the diffusion model. There is what we call the diffusion model using formation factor method to see or to calculate the instantaneous diffusion coefficient. This one that we use, normal one that we use, it is depend, like what can I call it? The one would not include like the porosity, like element, or like binder properties of the concrete. But with this method, we can use binder properties of the concrete, and we use there is when you have concrete, that I have to explain this to you before I continue. When you have concrete, actually, there is a change of, when you mix concrete, when it is hardened, you are curing it, there are some reaction that is happening inside the concrete. That is what we call, as I say, hydration and pozzolanic activities. This hydration or pozzolanic activities change the properties inside the concrete. So it changes what? The properties inside the concrete. So that changing of the properties increase the resistivity, or maybe the pore spaces may be wide or maybe close. So, but we need one that is closing the gap or the porosity of the concrete. So in this method, we use the fluid. There is fluid inside the concrete because there is water. When the water, there is some material inside the concrete that mixes with water. This means they form fluid. We know fluid. We are all engineers. Most of us are engineers. We know what fluid is. So there is inside the fluid, it changes the properties of the water. So in this, we use that fluid inside the concrete and test the resistivity itself. That is, it's more advanced than the one that I have reported before. I hope you are getting me, please. Maybe civil engineering based engineers may understand more. So after we use this formation factor method and calculated the resistivity, you can see. So the diffusion coefficient of this drop between 7 to 56 days, particularly for LC3 and FA. So